-1. Up today, we've got an introduction to lots of stuff. We're going to go over cylindrical coordinates, spherical coordinates, and very briefly touching on parameterizing surfaces. And we're going to somehow fit all of that into one Friday's lecture. It's going to be great. But once again, I am your host, Steve Dragoo, and let's learn some math. Woo. Okay, starting with cylindrical coordinates. First thing we're going to do. Basically, both cylindrical and spherical coordinates are an extension of polar coordinates into 3 dimensions. We've got 2 ways of upgrading polar coordinates because we just decided that we wanted to be difficult, I guess, and do it twice. I think cylindrical coordinates matches the 3D coordinate system we're used to the best, right? Basically just takes your regular old polar coordinates, which are r and theta, and adds a z-axis to it, and that's it. So it's really just the same polar coordinates we're used to from whether it was a trigonometry class or an advanced geometry class, or just when you revisited it in Calc 2 or possibly Calc PC, depending on which you're coming from. There's the same thing in Poly I. R and theta are going to be our 2 parameters in polar coordinates. R will be the distance from, well, it used to be the distance from the origin. Now R is going to be defined as the distance from the z-axis. Right, let's take a straight line over the z-axis because that's kind of like an extension of the origin, just up and down. So R gets measured from the z-axis now, which is the origin if you're in the xy plane. And theta is the same theta we'll be used to. We measure counterclockwise, starting from the positive x-axis. So that will not have changed at all. Now, since our x-axis comes out of the page at us, theta is going to start from there, and it'll measure, again, counterclockwise when viewed from above. Hopefully I did all of that demonstration right. And then z is e. Cool. So I think that about does it. When we list out our polar coordinates, we usually list them in order of r, theta, z, listed up there at the top of the page. And we have a few other definitions to talk about. But again, it should look pretty familiar from polar coordinates. X is still going to be r cosine theta, y will be r sine theta, z is z, and a couple of other useful identities here are that x squared plus y squared is equal to r squared, which is the equation of a circle, or possibly the Pythagorean theorem, depending on your point of view. They're the same thing, really. Turns out, I digress. And y over x is equal to tangent theta. Now, it is important that that's our definition for theta. Y over x is equal to tangent theta. And even that'll run into a couple of problems, but it's mostly fine. In particular, I'm making a stink because I want to talk about the note on the right side of the screen, which is that theta, by definition, is not equal to the inverse tangent of y over x. There are a few complicated reasons for that, but effectively, the tangent inverse function is not a very good function. It has a specific couple of jobs that it can do, but it has a very restricted range, meaning I can't get all possible angles out of it. So if you've seen me for trigonometry before, this will sound a bit familiar. The inverse trig functions are very good at finding reference angles, but they're not very good at finding solutions. So most of the time, if we're going to use an inverse trig function, we're going to have to think about where our angle should be and then adjust our answer accordingly. But as long as we take the inverse tangent or the inverse sine or the inverse cosine of a positive number that's within our domain, we'll get an angle that's in the first quadrant. And again, we would call those reference angles. To give a quick example, the reference angle of pi over 4 in the first quadrant is going to have the same x and y values as all of the other pi over 4 class of angles, right? So all of our blank pi over 4s are at like root 2 over 2, comma root 2 over 2, possibly with a negative sign on either the x or the y value, depending on which quadrant we're in, but they all have the same reference angle of pi over 4. Again, that's what the inverse trig functions will be good at finding. So just be careful anytime you use an inverse trig function. It probably requires a little bit of extra thought. So when I solved out this problem here, example 9.3, I got that tangent theta was equal to -1. And off the dome, I've got 3 possible angles that work for that equation. 3 pi over 4, 7 pi over 4, and negative pi over 4. Really, there's an infinite number of them because I can just repeat that pattern until I find more things. So I have to check what quadrant my point is in. And I've got a negative x value with a positive y value, which is quadrant 2. So I'm going to choose the angle that's in quadrant 2, 3 pi over 4. Notably, tangent inverse is incapable of providing me the answer 3 pi over 4. If I try to take the inverse tangent of negative pi over, or of -1, it's going to give me negative pi over 4 as an answer, which isn't the angle I want. So again, just be careful with your inverse trig functions. They're not very good at being, well, they're good at being functions. They're just not good at doing the thing that you want them to do. So just think a little bit when you're finding your angles. Great advice, me. Yeah. The other coordinate system then is going to be spherical coordinates. So if let's just start by looking at that diagram over there. Actually, I've got a slightly better drawn one over on the right. Or maybe I think it's slightly better drawn. It's got more arrows and stuff. So spherical coordinates. It'll look like this. If I'm trying to measure out to some point in space, say that this is going to be my point in space. Rather than finding how far in the x direction and how far in the y direction, how far in the z direction to go, I am going to first just figure out my distance from the origin. So this will go back to our radius being distance from the origin, so distance from the z-axis. I'll still measure theta the same way, figure out how far I needed to twist to get to that point. But now, instead of, I'm going to be a little careful here. Instead of measuring how far up the z-axis to go, I'll just measure out an angle from the top of the z-axis to my point. So over to here. Angle from there to there. Again, being careful with where I'm putting this point out in space. That new angle, we're going to call it phi. It's the blue one labeled on the diagram. And what do I want to say about phi? Again, it's measured from the z-axis where 0 degrees is going to be straight up. Meaning if I want to be in the xy plane, that'll be an angle of pi over 2 radians, or I guess 90 degrees, right? If I go from straight up to just flat, that's at 90 degrees, all the way to a maximum value of pi radians, 180 degrees, which points straight down. Suppose I could have kept my visual aid going there, but I don't know. So that, what else would we be saying about these points? We're going to redefine x, y, and z in terms of these new spherical parameters. But because we want to distinguish between the r value from cylindrical coordinates, we're going to call our new radius rho, or the Greek letter that roughly takes the place of r in the Greek alphabet, except it looks like a p. Sort of unfortunate, but I don't know. So rho is that p-looking thing that's in purple. Purple for rho. But so like we're gonna use that as our new spherical parameter and the same 2 angles that we just discussed. Switching over from cylindrical coordinates, I think goes over relatively well. So now let me go back over to the diagram that I'd drawn right here. If I'm expanding out what that radius looks like, just in a planar slice, you can see I've got my rho value in orange. Just kind of move that picture over to look at the 2D example for a second. where phi, again, blue angle, is going to be measured from the z-axis over to my new rho value, effectively the radius, but the spherical radius, with the two cylindrical coordinates making up the opposite and adjacent sides of the triangle, right triangle that's sort of implicit within our diagram. Z is still the up and down distance. R now is our out from the z-axis distance. And I can define both sine and cosine of phi. In particular, sine is going to be r over rho, and cosine of phi is going to be z over rho. Rearranging those for r and z, I would get the initial step to take me from cylindrical to spherical, which will be that r is equal to rho times sine phi. And then I'm just going to substitute those into my usual r cosine theta and r sine theta equations for x and for y. So I still have cosine theta for x and sine theta for y, but they've got a bit more stuff attached to them. So now it's going to be a rho sine phi on both x and y. And again, that sine phi is coming from converting our cylindrical r to our spherical rho. So that's the sine phi comes in from. And then we leave cosine phi to talk about the z value. And I almost forgot to go talk about our guidelines, so let's go do that. Again, these are going to be guidelines, not actual rules. But in order to cut down on repetitiveness, and so that we don't spend too much time trying to describe the same points, but with multiple parameters, where possible, we're going to use these, again, guidelines. I'm going to have rho be a positive number, so rho will be greater than or equal to 0. Theta, whenever possible, is going to be between 0 and 2 pi, so that's one trip around our circle. And phi, I'm going to contain between 0 and pi. Because as it turns out, if I want to talk about some point out in space, maybe it's this guy, and I want to talk about it with spherical coordinates, I could have my, say that this is at theta angle of pi over 3, right? And it's right here. One way to talk about it would be to say that this is an angle of pi over 3, but another way to talk about it would be to spin around in a full circle, come back to the same point, but now I'm at an angle of, this would be 7 pi over 3. And they both describe the same point, because I can spin around in circles as much as I like to, and then come back to facing the same direction. It's just a fun little quirk of polar coordinates that will still exist in cylindrical and spherical. So in order to have just a unique description of a point, we'll try to stick to these guidelines again. Staying within just one circle for theta, and staying in a half circle for phi. So that's kind of an interesting one. We should talk about that a bit more. So, since phi is mainly used to figure out where in the z direction we are, right? How far above or below the xy plane we're at, except we're going to measure it as an angle instead of just an up and a down distance. Phi angles that are in the first quadrant will be above the xy plane. Phi angles that are in the second quadrant will be below the xy plane. But I don't need to go any further than that. So I can talk about straight up with 0 radians, all the way down to straight down with pi radians. Which means if I say wanted to describe a point, well, how about a point that's red? Yeah, I'm going to put it over here. Oh, wait, no, I've been doing this all backwards. I think I wanted it over there for you guys. Yeah. We're going to keep going with it. If I'm trying to describe a point that's down here, say it's at an angle of, I don't know, 3 pi over 4 radians for phi. But I also wanted to talk about its symmetric point over on the other side, where I could extend my phi angle beyond pi to maybe talk about 5 pi over 4 radians being over on the other side of me. Again, just like figure out that symmetric point to go from one spot to the other. I could, again, extend phi so that it passes through the z-axis and over to the other side. But instead of doing that, I'll take my original point, which is at 3 pi over 4 radians, and just rotate theta all the way around until I'm over at the symmetric point on the other side that way. So by using theta to rotate all the way around the z-axis, we don't need z to go past pi. So theta, or phi, excuse me, phi is going to just be restricted to being between 0 and pi radians. Hopefully that demo made sense. Because at this point, I think I've talked enough in some platitudes, generalities. Let's just go do some problems. That's generally a better way to teach this stuff anyway. Okay, so let's look at some things. In particular, our first example. I'd like to convert this point, the Cartesian point or the rectangular point, root 3 over 2, negative 1/2 root 3, into both cylindrical and spherical coordinates. So let's do that. So starting with figuring out r, I'm going to go to my equation. That's r squared is equal to root 3 over 2 squared plus negative 1/2, also squared. And adding those up, I think I get 1. 3 over 4 plus 1 over 4 is 1. And I'll also set up my equation for theta. It should look like tangent theta is equal to negative 1/2 over root 3 over 2, which will be negative 1 over root 3. And now from that information, I want to figure out what r and what theta are going to be. So technically, r over here is plus or minus 1, because it could be either. And as a very strict rule, r can be positive or negative. But if we're trying to describe these points cleanly, let's try and use that as a definition. I'm probably just going to pick positive 1 for r. No, technically it could be either. But again, if we're following our guidelines, we're going to take r to be positive 1. I've also got to come figure out where theta is equal to negative 1 over square root 3, which will happen at 5 pi over 6 and at 11 pi over 6. Or I'm just grabbing these angles off of the unit circle. Because I still, have that in the brain pan. So if I've got to decide between those two angles, throw an or right there. If you go take the tangent inverse of negative 1 over root 3, it's going to tell you that the answer is negative pi over 6, which, while I guess correct, isn't within our guidelines of saying that I want 0 to be between 0 and 2 pi. So we're going to try to use one of these other angles instead. Notably, I see that my XYZ point is at a positive value for X and a negative value for Y. And if I've got positive X with a negative Y, that is the fourth quadrant. Quadrant 4. Highlight that. So if I'm going to be in quadrant 4, that means I want 11 pi over 6. Okay, come on. There we go. So at that point, I think I've got enough to put my coordinates together. I'm looking at the point 1, 11 pi over 6, and square root 3 for z. because I don't need to transform z out of my Cartesian point. It's the same value. Then, if I want to go transform this thing into spherical coordinates, relatively similar process. I'm looking at rho squared is going to be equal to x squared plus y squared plus z squared. So root 3 over 2. Let's try that again. Root 3 over 2 squared plus negative 1/2 squared plus root 3 squared. And adding all of that up, I got 4. Now, theta will not have changed from cylindrical coordinates. So I'll just bring that back down since I already did the work to solve for it. Theta is the same between spherical and cylindrical coordinates, so I don't need to solve it twice. But then to find phi, see, there's a few ways we could go about this. One of those would be that tangent of phi, there we go, is r over z. I know that sine phi was r over rho, cosine phi was z over rho. So if I do sine over cosine, I'll get r over z. I know that r is 1 and that z is the square root of 3, which means that phi is going to be pi over 3. Nope, pi over 6. Too many 3's. And why don't we start highlighting some of those pieces? I'll try to be clear about when I'm talking about theta versus when I'm talking about phi, because I know it can get a little confusing now that we've introduced 2 angles into our system. And if I want to come back here to figure out what rho was, again, technically could be plus or minus 2, but we'll just stick to positive 2 wherever we can. So our points in spherical coordinates is going to be 2, 11 pi over 6 for theta, pi over 6 for phi. Or maybe phi. I've heard it both ways. I like phi though, so that's what I usually say. Another example, considering the point 4, 5 pi over 7, 3 pi over 4, the product of its Cartesian coordinates, x, y, z, is positive. True or false? So, I am going to use a series of arguments about coordinates to try to answer this one. In particular, I want to look at the coordinates that phi and theta are in. And it looks like we're listing this point out as rho phi theta. But I know our textbook has it as rho theta phi. Be a touch careful with how the spherical coordinates get listed out. Sometimes they don't agree with each other. So just, yeah, heads up on that. Let's start with phi. So phi is in the second quadrant. Phi is in quadrant 2. Let's use Q2 to represent that. 5 pi over 7, right? That'd be in quadrant 2. If that angle is in the second quadrant, that means that z is negative, right? Because I've moved my angle down into the second quadrant, which will be below the xy plane. So z is negative, meaning I've got a point that is something, something, and then a negative value. What those numbers are, I don't super need to worry about. I just need to know if z is positive or negative. Go do the same thing with theta. So theta is 3 pi over 4, which means it's also in the second quadrant. So I'm looking at a point that goes negative, positive, something. Because theta is just going to tell me the sign of x and y, but it won't tell me anything about z. But now I know enough to at least figure out the sign of my product, x, y, z. I know that it'll look something like a negative number times a positive number times a negative number. And if I take that product, I get something positive, since two negatives make a positive. Right. So in the end, I found that that statement was true. The product of the Cartesian coordinates for that spherical point should come out to be a positive value. So, given that we can convert points, let's try to convert full surfaces. So changing over an equation to being in cylindrical coordinates or in spherical coordinates. In particular, we've got this set up here. Z is equal to the square root of x squared plus y squared, which I believe is a cone. But if I wanted to change that over to cylindrical coordinates, I would say that z is the square root of r squared, since x squared plus y squared is r squared. Which means that z is, if I'm being extra careful here, z should be equal to the absolute value of r. If I take the square root of r squared, my result should be absolute value of r. But I could also rearrange this to just give the easier looking equation, probably the one that you came up with, is just z equals r, strictly saying that r is greater than or equal to 0. Because if I look back at how the cone is defined, z is only the positive square root of x squared plus y squared. Z, no matter what, needs to come out to be a positive value from my original definition, which means while this thing is a cone, it is only a half cone because it'll take the top half and not the bottom half. Just, be a touch careful with that. But that gives us our equation, z equals r. That's the equation of a cone in cylindrical coordinates. Theta doesn't need any explicit definition for that function, for that surface. To go do the next bit, switching this thing into spherical coordinates, I suppose I could start from z equals the square root of x squared plus y squared. Let's just jump that to z equals r, because we already converted that step. And we'll just, know in our hearts that r needs to be a positive value. And I'll convert those two bits into spherical coordinates. Z, I know, is rho cosine phi. And R, I know, is rho sine phi. Let's try and keep my equal signs lined up. And again, I'm specifically looking at the phi angle, which is the one measured from the z-axis. And I want to simplify this thing. So I'm going to divide everything over to the right side, which will give me rho sine phi over rho cosine phi. which simplifies to just tangent of phi. Right, sine over cosine is tangent, and those rows can divide away. Just one. So it's technically we've got to be careful if rho is equal to 0, but we'll worry about that later. And finally, if I've got 1 is equal to tangent phi, I can solve that equation. Phi should be pi over 4. And then ultimately, that's the equation of my spherical cone. It ends up being just phi equals pi over 4 in its simplest form. I know there's at least one web work problem that'll ask you to solve an equation like this one, and it won't be happy until you reduce it down to something like that. Something where it's just phi equals an angle, phi equals some number. And why don't we identify a couple of surfaces from their cylindrical and spherical equations? In particular, we're going to choose from the options listed here, A through E, a plane, one of the two types of paraboloids, just a cylinder or possibly a sphere. So let's try that. Starting with z equals 4 minus r squared. Stop up. Z equals 4 minus r squared. And I want to get that in terms of the way that I know how to recognize equations, which for the most part is back in Cartesian coordinates, because we already did that quadratic surfaces lesson. So if I had this in an x, y, and a z equation, I could probably figure out what kind of shape it is. So I'll just substitute back in, call this 4 minus the quantity x squared plus y squared, which is 4 minus x squared minus y squared. And if I'm going to try to identify that surface, I see that I've got a single linear term mixed with a couple of square terms. So I believe this ought to be one of our paraboloids. Since I get a parabolic shape if I've got a linear term equal to a square term. So I'm thinking it's one of the paraboloids. I notice that both of my square terms, x squared and y squared, have the same sign, which means I think that's going to work out to be elliptic rather than hyperbolic. I think that's enough information to claim this thing is an elliptical paraboloid. In particular, it's one that opens down instead of up. It's also been shifted up the z-axis 4 units. I just apply some linear transformation to that equation. The other one, I think it's a little more exciting. Let me start with rho. Rho is equal to sine phi, sine theta. Call it blue and green for the two angles that we have. So anytime I see one of the trig functions sitting by itself, I usually like to have a rho attached to them or an r attached to them, depending on which system I'm coming from. Same thing if I see just a plain radius sitting by itself. Usually I like to have it as the radius squared before I start trying to substitute some stuff in. So my first step, rather than direct substitution, is going to be to multiply this whole equation by rho all the way through. Because that'll then give me the equation rho squared is equal to rho sine phi cosine theta. No cosines in this problem. Highlighting that Those two rows came from me just wanting to multiply it in. Because now my substitutions are a lot nicer. I have an equation for rho squared. Move that over. I know it's x squared plus y squared plus z squared. And on the other side, I've got rho sine phi sine theta, which is a direct substitution for y. So it's nicer than trying to substitute each of those elements individually, I think. So I did it this way. And then I can simplify this equation by completing a square. I would get x squared plus y minus 1/2 squared plus z squared. And in order to complete my square, I would have needed to add 1/4 to both sides. So I think from that equation, I can recognize this thing as a sphere. Option E. Okay. Moving right along. Talking briefly about maybe how we would sketch some of these shapes in our three coordinate systems. I'm gonna just kind of touch on this part briefly. So I already drew the shapes out ahead of time. If I wanted to draw the cone, which I think at this point I've looked at the cone as three different equations. Drawing a cone in Cartesian coordinates, I know that z equals square root of x squared plus y squared looks like some circles. So I drew in several concentric circles that increase in radius as I go up the z-axis. That's what I would expect drawing from Cartesian coordinates. If I'm going to instead draw these things in cylindrical coordinates, I want to draw in a bunch of points where z and r are equal to each other, is what I've attempted to demonstrate in this diagram. So drawing at a point where z and r are equal and then revolving that point around the z-axis. Right? I just spin it around the z-axis, I get a circle, because that's generally what we get when we revolve points around an axis. So you think back to like surfaces of revolution from Calc 2, we aren't really going to get into that, but it's a way to think about how we're generating these shapes in cylindrical coordinates. To rotate it around the z-axis. And if we're looking at constructing that cone in spherical coordinates, we get, I think, maybe the easiest of them all. I just measure a line out from the z-axis to an angle of pi over 4, or whatever my angle might be, and then again rotate that thing around the z-axis to come up with a cone. Three different ways of thinking about 3D space. On that topic, just want to look at a few basic shapes and their equations in spherical coordinates. Some of them, I think, make some rather intuitive sense. If I just have rho equals a number, like rho equals z, maybe rho equals 2 or rho equals 7, I get a sphere. Right? If I'm in spherical coordinates and I just define my radius to be a number, that'll give me a sphere with that radius. Most intuitive shape that we'll look at all day, I think. We're also going to define the idea of a half plane, which is just theta equals some number. And we're going to look at it being a half plane specifically because we'll use our guideline that r should be a positive number. So if I fix theta to be an angle, call it pi over 3 radians, my half plane is just going to extend along the line where theta is equal to pi over 3 radians. But now it's a plane instead of just a line because I'm stepping this up to 3 space instead of just a flat plane. Blah, blah, blah. And on to the one that we just looked at, which was a cone. We get that equation if we just set phi equal to some number. Phi equals just some angle. Up in cylindrical coordinates, couple of things. Z equals R by itself is a full cone, both the top and the bottom half. Which is why you have to be a little bit careful with the equation Z equals R if you started like we did, where we started from Z equals specifically the positive square root of x squared plus y squared. We have just Z equals R, we get the full cone. But then also cylinders are the cylinders that we would expect. Set R equal to a number, and you get a cylinder as opposed to a circle or a sphere. Anywho, back to the last topic, which is going to be a very quick crash course into parameterizing surfaces. Because these cylindrical and spherical coordinates are really just a way of parameterizing shapes from our original x, y, and z components. We've looked at parameterization a little bit already, where we had, what did we usually parameterized some curve, or maybe it was a line where we used a single parameter t to describe x, y, and z. If we're going to describe a surface instead, a surface being a thin two-dimensional shape that maybe curves through free space, it's going to have more than one dimension that it can exist in. So, everything all right back there? Gotcha. Distracting? Odd. All right, who remembers what I was talking about? 'Cause I don't. Thin 2D surfaces. Thank you. So I want to talk about thin 2D surfaces that curve through 3 space. Because they're two-dimensional, I'm going to argue that they're two-dimensional, I need more than one parameter to talk about them. Right? If I just wanted a line or a curve, one parameter was fine because I could only move in one direction, either forward or backward. But now for a surface, I can move in 2 dimensions, 2 directions. So I'm going to need 2 parameters. That's the big fancy explanation of parametrizing surfaces. In particular, if we wanted to look at our half cone given by z equals r in full, we could write out the equations. X equals r cosine theta. Y equals r sine theta. And z equals r. To define the whole bit. So now I've got x, y, and z expressed only in terms of r and theta. I only needed 2 parameters to talk about that shape because it's a surface. My 2 parameters here are r and theta. But because we like to make things complicated, we're going to redefine our parameters to just be s and t instead of r and theta. So it looks like the parameterization of a line where we only used t as our parameter. So that we have x equals s cosine t. Y equals s times sine of t. And z equals s. Where my 2 parameters are, again, s and t. One of the main reasons we do that is that it's kind of hard to write out the vector equation. R of s and t equals r cosine theta, r sine theta, r. Because now I'm using r too many times. All right, so And at least that's the way that the textbook likes to describe these things, is just re-parameterizing to be S and T instead of R and theta. But since variable choice names don't really matter, you can choose to use whatever letters you want. Either version of the parameterization is fine. Just know that a lot of the examples that you're going to see are going to use S and T as our two parameters. Ta-da, ta-da, ta-da. Right. Let's go look at a parametric surface. Again, given by the vector equation. R of S and T is equal to S plus T, T minus 3, and 2S minus T. With S and R in the real numbers, find the point that corresponds to the parameter values 5, 2. Well, I can just plug 5 and 2 in to get a value. This looks like 5 plus 2. 5 minus 3. No, nope. Try again. 2 minus 3. T is the second parameter. And 2 times 5 minus C. Let's call it 10 minus 2. So that's 7, -1, 8. Right. I just plug some stuff in. A follow-up question might be to ask, is the point 1, 2, 3 on this surface? Well, let's find out. If I want to check if it's on the surface, I should just set them equal to each other. So how about 1 equals S plus T, 2 equals T minus 3, and 3 equals whatever the last one was, 2S minus T. 2S minus T, not 2ST. And now I've got a system of 3 equations that I want to solve. So what I'm going to do is I'm going to solve a system of 2 equations and then check it against the third to see if this thing fits. So I'm going to start from the easiest one, which is in the middle. I get that T has to be equal to 5. It's my only choice. From there, I'll plug it into the equation on the left. 1 is going to be equal to S plus 5, which means S is -4. So maybe I'll color that in blue, color that one in green. Draw a quick arrow from here to there to kind of illustrate what I did. And now that I know my 2 parameters, need to be 5 and -4, I'll check it against the third equation, which should be 3 equals 2 times -4 minus 5. Giving me the equation 3 is equal to -13. And last I checked, 3 and -13 are not equal. So our point 1, 2, 3 is not on the surface. If I were to try that again with a slightly different point, 5, 0, 1, the setup is very much the same. 5 equals S plus T, 0 equals T minus 3, 1 equals 2S minus T. So 3 is T, meaning that 5 is S plus 3, or 2 equals S. Highlight my two values. And then check that against the third equation. I think this time I find out it works. 2 times 2 minus 3. And I get the equation 1 equals 1. Yarp. It's on the surface. All right, and that does it for today's lecture. Bye-bye.